Hey guys, today we're going to learn basic differentiation, and up to this point we have been taking derivatives by using the limiting process, and it could be a lot of work to evaluate the limit over and over again. So that's why we're going to find faster techniques to take derivatives rather than using the limiting process. So I just want to talk about some notations for derivatives, and the first notation is Leibniz notation. Leibniz was one of the two people who invented calculus, the other one was Newton. So the first derivative could be represented as dy over dx. And say if I have y is equal to f of x for some arbitrary function f of x, then dy over dx would represent f prime of x. And dy and dx are things called differentials, and dy means a small change in y, and dx means a small change in x. So y over x represents slope. So therefore, dy over dx also represents slope, but it's a small change in y over a small change in x. And this makes sense considering our definition is to limit the distance between the 2 points. We want small changes. So you could also take multiple derivatives of a function. So the second derivative would be the derivative of the derivative of y, and the third derivative would be the derivative of the derivative of the derivative of y, and you could do this as many times as you want. So the second derivative is notated as d squared y over dx squared. I wouldn't worry about why the 2 is placed where it is. You don't need to worry about all that. And the nth derivative would be represented as d to the n of y over dx to the n, just like that. So you might see the actual function being plugged in rather than y, just like this. And it's the same exact notation. The only difference is I'm using square brackets and I'm plugging f of x in for y. Nothing different. And then the next one is Lagrange notation, and this one we've seen before. It's just f prime of x. The second derivative could be represented as f double prime of x. The nth derivative could be represented f parentheses n of x. Sometimes you might see y being plugged in for f of x, y prime, y double prime, y parentheses n. And then the final one is Newton notation. You might not see this one as much as the other ones, but you might see it occasionally. And that's represented as a dot on top of the y. So the first derivative is y dot. Second derivative, you see two dots, so y, two dots. And the final one, you might see y dot, but you'll see an n above that, indicating how many derivatives to take. So I want to start by talking about derivatives of constants. And the derivative of any constant is 0. And you can see below I wrote d dx of c is 0 for some constant c. And this is what I meant when I said you could plug the function in directly rather than writing dy over dx. The derivative of 87 is 0. The derivative of some cosine and natural log number is 0. And y? Constant functions are just lines with slope 0 for all x values, as you can see with the black line and the graph. You can see how it's just a horizontal line. The slope is always 0, so when you bring 2 points closer together, it should be 0. And when I change the constant, all I'm doing is moving the graph up or down. I'm not changing the way it increases or decreases. It's still going to be a flat line. It's still going to have slope 0. So that is why a derivative of any constant is always 0. So the derivative of any linear function is just the slope. And why? Linear functions are just lines with constant slope m. And as you can see in the graph below, you could just see the line with constant slope, the same thing we've seen from Algebra 1. And I think I mentioned this in the first video, but what differentiates a line from a curve is while a curve has different slopes at different x values, its slopes varies as the x values vary. For lines, it always has one constant slope for all x values. Therefore, it's going to have a constant derivative. So for instance, the derivative of just mx plus b is just m, its slope. The derivative of 4x is 4. The derivative of 5x minus 7 is 5. The next one has a slope of 4 square root x, 4 square root of 10. So its derivative is just 4 square root of 10. The next one, its slope is 3 times 4 over 9, which is 4 over third. So the derivative of any linear function is just its slope. So the derivative of a power function x to the n for any constant n is n times x to the n minus 1. So basically you bring the n out in front and you subtract 1 from the exponent. So for instance, the derivative of x cubed is 3x squared. You bring the 3 out in front, you subtract 1 from the exponent. The derivative of x to the fifth, you bring the 5 out, it's 5 times x to the 5 minus 1, 5 times x to the fourth. And finally, you have the derivative of x to the sixth, you bring the 6 out, so it's 6 times x to the 6 minus 1, or 6x to the fifth. So why this is stems from the definition of the derivative. And you have to manipulate the definition of the derivative and plug in f of x equals x to the n and manipulate from there. For time, I'm going to spare you the proof, and this is how we end up with the power rule. So now I want you to take some time to find the derivatives of these functions. Y is equal to the square root of x, f of x is equal to 1 over x squared, y is equal to 1 over x times the cube root of x, and y is equal to x to the e over x to the pi times x squared. And it'll also give you some practice with the notation. And I'm going to give you a hint. Remember, the derivative of a power function x to the n for any constant n is n times x to the n minus 1. So I want you to pause the video and try to solve these 4 problems. Now remember, for any constant n could be any number. It does not have to be a whole number. For instance, you could have a negative number up there. The derivative of x to the negative 7 is negative 7 times x to the negative 8. You could have a square root up there. The derivative of x to the square root of 2 equals square root of 2 times x to the square root of 2 minus 1. You could even have a tangent inverse of 2. This is a bit crazy, but I don't think you'd see anything like that, but if you do, you could just use the power rule. You might have natural logs up there. That seems more probable than the tangent inverse, but it doesn't matter because the derivative of any number n that's there, x to the n, is always n times x to the n minus 1. It doesn't matter what n is, you're just following the same process. It doesn't matter whether you see tan inverse, natural logs. So my main point is don't get intimidated by the constants there. Just follow the process. So let's start with y is equal to the square root of x. So we need to manipulate this in a way such that we have x to the power. And we don't have to do much manipulation, as we know from algebra that this is equal to just x to the 1/2. So from there we take the derivative by using the power rule. We bring the 1/2 out in front and we subtract 1. So we have 1/2 x to the negative 1/2. And then I added this optional step, which I went and took the x to the negative 1/2 and brought it back down into the denominator. And you might not need to do this. If you're taking AP Calculus, in fact, whether A, B, or BC, I would highly recommend you that you just leave it as 1/2 x to the negative 1/2. However, there are some people which may want you to go and bring the x into the denominator, since I started out as a rational function and they might want you to bring it back down as a rational function. However, if you're taking AP Calculus, I would just leave it as 1/2 x to the negative 1/2. You don't have too much time. The next one is f of x is equal to 1 over x squared, and we once again need to manipulate this in such a way such that we have x to some power. Well, we could do that just by rewriting it as x to the negative second power. We take the derivative, we bring the negative 2 out in the front, we subtract 1, negative 2 times x to the negative 3. And then once again, I added the optional step of bringing it back down into a denominator, negative 2 over x cubed. But once again, you could just leave it as negative 2x to the negative 3. That is fine. In fact, in the future, I'm just going to leave it as a negative exponent. But I just wanted to show you that some people might require you to bring it back down in the denominator, and so it depends. So the next one we have is y is equal to 1 over x times the cube root of x. And we once again need to manipulate this such that we have x to some power. Now this time it's a little bit more manipulation. So we have the cube root of x is equal to x to the 1/3. But we gotta multiply it by x. We want one exponent only, we don't want two of them. So 1 plus 1/3, we get 1 over x to the 4/3. We have 1 over something, so we could reciprocate it and add a negative. So we have y is equal to x to the negative 4/3. And now we're ready to take the derivative. And we have dy dx is equal to negative 4/3 times x to the negative 7/3. And finally, the last one is y is equal to x to the e over x to the pi times x squared. And this just tests to make sure that you're not intimidated by those values, e and pi, because remember, they're all just power functions, which we could just use the power rule. So first thing is we need to combine the two exponents in the denominator. So x to the pi times x squared. So we end up with y is equal to x to the e over x to the 2 plus pi. Now notice we have something in the denominator. We could reciprocate that, and we'll end up with y is equal to x to the e minus 2 plus pi. Since we're dividing by something, we could subtract by 2 plus pi. And from there, we can just go and take the derivative. Now there should be a bracket there. It should be dy dx is equal to bracket e minus 2 plus pi. And then we subtract 1 from the exponent. We multiply by x to the e minus 2 plus pi minus 1. And we could probably clean things up a bit. So I just decided to distribute it, and we end up with dy dx is equal to e minus pi minus 2 times x to the e minus pi minus 3. And that is our final answer for that. We just apply the same rule. It doesn't matter whether we have e in the exponent, pi in the exponent, it doesn't matter. We're still applying. So one final note, this applies to the first problem, is that I would suggest you not to rationalize the denominator. I am even very hesitant in bringing the x to the negative 1/2 down to the denominator and turn it into a radical, but I would very much wouldn't want you to rationalize the denominator unless a teacher asks you to do so. And one reason why is, say if I asked you to find the x value at which the slope of the tangent line of y equals square root of x is 1/3, what you would do is you'd set dy over dx equal to 1/3, or you'd set 1 over 2 times the square root of x equal to 1/3. That's pretty easy to solve for x. However, if you rationalize the denominator, now you would have square root of x over 2 times x equal to 1/3, and that's harder because you have x terms in the numerator and in the denominator, so that's going to be much more hard to solve, and also it requires a lot more work. If you just leave it as a negative exponent or just bring it down, it requires a lot less work. However, you have to take the extra time in multiplying square root of x over square root of x, which you might not have time to do in the AP exam. So I highly suggest you to not rationalize the denominator unless you absolutely have to. So next we have derivatives of some special functions. First, we have the derivative of e to the x itself, and that's one thing that makes e to the x unique. It has its own derivative, as you can see. The next one is the derivative of sine of x is cosine of x, and derivative of cosine of x is negative sine of x. So I would really want you to memorize these three derivatives. Very important. It'll make it a lot easier when applying them to the more complicated functions. And if you're wondering where the derivatives of other functions are, like where's tangent of x, cosecant, secant, cotangent, or what's the derivative of 2 to the x or natural log of x, stay tuned. 2 videos from now we talk about the quotient rule. We'll introduce the derivatives of some other functions there. Next video, chain rule. We'll introduce the derivatives of some other functions there. Just stay tuned, they're all coming.